cutoff, saturation, and linear mode, right? And the conditions that set these things for a MOS is a little more complicated than it is for the BJT, no? For MOS, we have na in order to start in cutoff, the MOS cap right here, no? And in order to get out of cutoff, the MOS cap must be inverted, no? In the inversion region, which means that the gate to source voltage must be greater than VTH. Or rather, well, okay, yeah. Basically, no? VGS is greater than VTH, dapat for cutoff, right? For us to get into saturation, we have two conditions, no? Well, okay, for cutoff, VGS is less than VTH. For not to be in cutoff, we have to be greater than VTH in the VGS, no? So that means this thing is kind of above 0.4, 0.6, 0.8, whichever the VTH is. They have varying threshold voltages. Anyway, for now the difference, no, between linear and saturation is one thing, no? The drain to source voltage, that is this thing, no, has to be greater than the difference between the gate to source voltage and the threshold voltage, no? Which it usually will be in your circuit so long as VGS is not very high, no? So for linear, you have that the VDS is less than VGS minus VTH, no? So what can we observe here? Kapag tumaas si VGS, no? Then you are in danger of getting out of saturation. Bakit? Kasi uh let's talk about in an example. Sige. So let's draw the circuit that we'll be talking about today, no, mostly. So, no? So meron tayong VDD, meron tayong RD, then meron tayong input voltage and output voltage, no? So you can observe in this circuit many things, no? But let's observe this, no? If we increase V in, of course, that is directly VGS, no? V in is VGS, right? If we increase VGS, of course, tataas tong current na to through the MOSFET equation, no? Assuming that we're in saturation, no? We are talking about saturation right now. The equation would be Kn over 2 VGS minus VTH squared. We see that if VGS increases, the drain current should increase. Di ba? So if VGS increases, the drain current increases, lowering VDS. No? So if VGS increases, VDS decreases. No? But the condition for saturation is that VDS has to be greater than VGS minus VTH. No? So the more you increase the input voltage in this circuit, the more you get out of saturation. No? The more in danger of turning linear you are. And in fact, no, the equivalent of a BJT, no, kasi 'di ba yung sa BJT, we want to avoid falling below 0.2. Sa MOSFET, we want to avoid falling below this thing, no? We want to avoid falling below VGS minus VTH. So medyo mas liquid yung condition for MOSFETs, no? And essentially, once we fall below that value, we go we get into the linear or the triode region, no? So then, that paints a picture, no, of what we're supposed to expect dun sa transfer function nito, no? So the transfer function of this circuit, again, a transfer function would be V out versus V in, no? So we're going to expect a few things, right? We have a threshold voltage, no? Before which, no? VI is VGS, by the way, right? We know that from this, no? VI is VGS. So we're waiting for VGS to be greater than VTH up here, no? We're waiting for it to be greater than VTH in order to escape cutoff. And then it successfully escapes cutoff, no? It goes into, of course, saturation. Bakit saturation yung una nating mapupuntahan? Well, we know that the higher VG is, the more in danger we are to get out of saturation, which means we are in saturation because VGS is as low as it can be here, no? Eventually, though, from saturation, we will transition to the linear region. And in fact, this would be directly diagonal, uh, the intersection of this transfer curve with the diagonal of the from the VTH. And why is that? Kasi this point would be at this point, no, VGS, because this distance, di ba? This distance is VGS minus VTH, no? Of course, because VGS is V in, no? So then, that means that here, no, VDS is equal to VGS minus VTH if we intersect this diagonal, no? So that means the edge of saturation will be here, no? At the diagonal coming from VTH, no? The one slope diagonal. All right? So that paints a picture of how we expect the basically the common source MOSFET biasing to happen, no? So let's talk about where we want to be here. Essentially, since we're operating this as an amplifier as well, no? Since we're operating this as an amplifier as well, we can choose a Q point, no? A quiescent point or a DC bias point for us to operate our amplifier. And this choice is important, no? Again, between points, between points A, B, and C, which one has the highest gain? So if we ask ourselves that, then of course, since gain is the slope of the transfer function, then we get that the highest gain would be at B, no? The highest swing would also be at B, no? Kasi our signal can travel from here to here, no? From B, right? If we choose A, no, we get no gain at all because the circuit is in cutoff, though the small signal would get you a little near saturation. A small signal like this, no? So An oscillation like this from the input voltage would cause an oscillation like that in the output, no? Which is kind of bad, right? In point A. So we don't want to bias ourselves at point A, right? So just like before, for MOSFETs as well, no? We can talk about the load line. So again, what is the load line, no? Well, kasi, what we can interpret, no, the load line as um, is because the MOSFET, no, follows, well, okay, this amplifier, rather this common source amplifier, because the ground is connected to source, the common source amplifier follows two rules, no? So circuit follows two rules. We have that um the ID versus VDS curves of the MOSFET, and we also need to follow the KVL at the output loop, no? Quite simply, these are your two equations, no? We have ID is equal to K N over 2 VGS minus VTH squared. And we also have VDD minus ID RD will be equal to your VDS, no? Of course, let's add 1 plus lambda VDS din dito, no? So these are rules that your MOS has to follow. Now, if you have systems of equations, a solution to that system of equations will be intersections of the graphs of those equations, no? This is something we know from high school math, hopefully, no? Because we skipped the math part in college. Anyway, so what we would have then is this thing causes this line, no? This is the output characteristic of your MOSFET, no? And the load line is, well, of course, a line, no? Because it's a linear equation, no? So, if this is your VDS and this is your ID, no? The load line would be like this because if VDS, no? Let's say that ID is equal to 0, then of course, V out would be VDD, right? Kasi walang voltage drop si RD. No? And likewise, if VDS was 0, ID would be VDD over RD, right? And so since our circuit follows these two rules, we know that the quiescent point has to be in between, in the intersection of these two rules that the circuit follows, right? So let's talk about, you know, certain things that happen in the circuit when we change uh, parameters of the circuit, no? So we know that increasing VGS, no, leads to increasing ID, no? Because ID is Kn VGS minus VTH squared, right? So we can draw something like this, right? So if we increase VGS, no, we go from the bottom BJT, the bottom MOSFET output characteristic to the top MOSFET characteristic, no, in a quadratic manner. By the way, no, as a trivia, you can draw a quadratic here, no, and that quadratic would tell you the edge of saturation, no? So you'd be at linear here, and you would be at saturation here. Why is that? Well, because no, VTS has to be greater than VGS minus VTH, no? Which leads to the condition changing as you increase VGS, no? So the difference between linear and saturation is actually a quadratic plot. Well, anyway, um, now what have we achieved? No, by increasing VGS. Well, what we've achieved by increasing VGS is we moved the state of the circuit from this place to that place. No? Kasi yun na yung bagong intersection ng load line at saka nung rule na follow nung MOSFET. No? And we can observe that we went from, well, actually, we were quite at the edge of saturation already. So when we increased VGS, tumaas si ID, causing us to fall out of saturation. No? Sige. So now from there, let's further change the circuit. No? So we've experimented with changing the input biasing. No? Now, let's try changing the load line. Yes, the load line. No? And how do we affect the load line? Well, since a line is uniquely identified by 2 points, no? We have to change either this or this, and we will have a unique change in the line, no? So, if we change RD, no? Let's say, for example, that I increased, let's make it green. Let's say, for example, that I increased RD, then what happens is, no? Kapag tumaas si RD dito, of course, this value goes down. No? The overall value of that goes down, which means na bababa itong hmm, y-intercept natin. Di ba? Tapos, hindi gagalaw yung x-intercept natin. Of course, kasi VDD yun. No? It doesn't depend on RD. So, this is our new load line. No? Which tells us na nag-move yung quiescent point natin from there to here. No? Which looks suspiciously linear because it is, right? Kaso essentially, nung binago natin si RD, we moved the load line such a way na bumaba yung y-intercept niya, and nakita natin, tinignan natin kung nasan ulit yung intersection ng dalawang rules natin, which is akin, no, to solving the system of equations, no, and found that we moved the biasing to this new point, the green point, no. So lastly, no, on the topic of the load line, Lastly, on the topic of the load line, we can have, um, we can change VDD, no? So if we change VDD, if we were to change VDD, let's say for example, tinaas natin si VDD, then of course, this thing and this thing are going to change proportionally to each other, no? A 2 times change here would be a 2 times change here. I hope that makes sense because this is just, you know, it's just 2 times VDD. Since 2 times ito, then 2 times din to, no? Which tells us that an increase in VDD is just an exact shift in this line, no? Because both intercepts increase proportionately, no? So now what do we get from this? Well, our intercept, no, of the two lines. So this is, if VDD increased, this would happen to the load line. So our intercept now changes from here, no? So from the white point to the green point here, no? And we're now deeper in saturation, no? Now, one could interpret this, no? As saying that when you increase the VDD, you allow more real estate for yourself before falling out of saturation, no? Of course, kasi nakita natin dito, as soon as we increased VGS, we fell out of saturation. And that's because the load line is very low here, no? If we increase VDD, na itataas natin yung load line, which means na we have more space before we fall out of saturation, and we can further increase ID, no? Which generally tends to increase your gain, no? And you see how we actually calculate the gain in the next lesson, no? Module 6. But Module 6 is not part of the midterms, no? Okay, so any questions about this so far? So basically, that's the concept of the load line in terms of the common source MOSFET amplifier, no? So, okay. So in terms of biasing, no? Let's think about it. When you have an IC, no? Well, typically, no? Let's talk about like some of the most used IC, no? Actually, sige, Google ko na lang para makita nyo. Diba? Snapdragon source voltage. Yan, sige. So this is some random Snapdragon chip, no? So we have a supply voltage range of 2.4 to 4.8, no? And in fact, dun sa Snapdragon chip, no, you have like, 50 pins, no? But we don't usually have um that kind of leeway, no? Kasi bawat pin na nilalagay mo dun sa IC, no? So kung ito yung spider mo, bawat paa sets you back like 3 million. Anyway, no? So we do not have the luxury of having multiple voltage sources, no? So typically for our amplifiers, no, we only have VDD, really, no? We do not have the luxury of setting a specific VIN in order to choose our bias point, no? Like we did here. Kasi dito sa ginagawa natin dito, of course, we were setting VIN in order to control the the position of this thing, right? Like the position of this thing depends on Vin, no? Which is VGS. When we increase VDN, we increase VGS, we increase the ID, and we change the biasing of the transistor, no? Well, of course, we can also change the RD, no? But we still need some sort of voltage at Vin. We can't let it be zero, right? Because zero means you'll be here, no? You'll be in cutoff. But when we bias Vin, no, we don't usually set a specific voltage to it kasi mahal ang isang extra pin, no? Um, basically, the slides also say, no, that it's impractical to put in a bias pin on your IC, no? It's expensive, no? So we not only have the VDD, which is typically 2.4, no, for the internal circuits, no? We only have the VDD for our circuits, no? And we must learn to bias our circuits such that VDD lang yung ginagamit natin. And typically, no, a way to do that would be to create a voltage divider, no? So let's talk about voltage divider bias. So as you may guess, no, voltage divider is just you set the voltage at Vin by simply placing two resistors here. No, you have R1 and R2. This is your RD. The voltage divider, no, created by R1 and R2 creates a voltage here, which is VDD times R1 over R2. No, and this creates a Vin, no, a large V, capital N, no, for your circuit, a DC Vin. Now, if you're going to ask me, okay, paano pumapasok yung small signal na thing natin dito? Well, because our small signal thing has a high frequency, then this acts as a short to it, but it decouples the DC bias circuit from our circuit. So maglalagay lang tayo ng capacitor doon and dito. Hmm. Okay, R1 over R2 plus sorry, baliktad yung voltage divider ko, no? So R2 over R1 plus R2. Right? And this would be the voltage at that point, which would be now our capital V, capital A. This would be your small v, small a, right? So this could be a way in which we bias our circuit, no? So when we want to bias our circuit like this, no, we have a few considerations, no? I remember when I did my 52 project, this is how I created the input stage, no? Well, actually, well, okay, BJT yung ginamit ko. Tapos meron pa akong isang resistor dito, which actually tends to make it more stable but while sacrificing the gain, no? Kaso, I'm pretty sure I've talked about that one in the BJT session naman. Anyway, considerations, no? Well, since we have this circuit now, we have some rules, no? For R1 and R2. We know the Vin we want, no? The capital V, capital N. Kasi meron tayong desired, quiescent bias point, di ba? We know that we can arbitrarily choose one here and we want to target that one, no? Which means that we choose a specific Vin. Of course, the x-axis here is Vin, no? So we choose this, no? We choose this Vin to get to point B, no? So we know the Vin. So, since we know Vin, this is one of the equations that could help us determine what R1 and R2 should be. No, this is a relationship between R1 and R2 that we have. Next is also power consumption. For a MOSFET, no, it's quite easy to do this. Bakit? Kasi hindi pumapasok yung current dun sa gate, no? So, we know exactly the amount of current passing through pababa dito, no? This current would be VDD over R1 plus R2, quite simply. Diba? Bakit po in-ignore yung capacitor para sa VN? Capacitor, no, we're doing DC analysis for biasing. Capacitors in DC, this would be an um, open circuit. Yes. No? So, that's the reason why we ignore the capacitor. But in reality, we're going to, if you were to implement this in a breadboard, no, you would need this capacitor in order to make sure that the SIGGEN, no? Kailan nyo ba si SIGGEN? I-SIGGEN, tapos may mga options ka, sabi mo gusto mo sinusoid, tapos ilalabas niya sinusoid, tapos lalagay mo yung banana plug dito, or alligator clip, whatever. Actually, banana to alligator. Tapos nakalagay siya doon. So to make sure that this thing does not interfere with your biasing, you put in a capacitor. Para sure ka na small signal lang yung pumapasok dito, and dito yung large signal yung and you can have your safe DC biasing dito sa area na to. Anyway, we're going to know a power consumption, no? Well, the current through R1 and R2 is simply VDD over R1 plus R2 kasi decoupled siya, no? Wala to, right? So, what we'll have is VDD squared over R1 plus R2 is the power consumption. And then we discover, no? The power consumption, if we increase R1 and R2, no? Increasing R1 and R2 lowers the power consumption, no? So we would want as much as possible na mataas si R1 at si R2. Right? So that's another thing that we consider, no? So typically we choose in around the thousands range for this one. Though I'm pretty sure my consequences yon um in terms of the gain, no? You'll see that dun sa kapag nasa actually topic 5 pa lang pala yung two-port networks, no? Topic 6 after the midterms is when you'll realize kung bakit hindi natin gusto masyado mataas din to, no? Kaso those are problems with loading, no? Anyway, those are the considerations for the um a voltage divider biasing circuit, no? Now, cons, no? Why don't we usually use voltage dividers for biasing circuits? Well, that's not true, no? Ginamit ko siya sa project, no? And that's what everyone used for the project. It's not just me. So it's fine, no? But your problem is, no? Sa project, pwede siya. Sa lab, pwede siya, no? Sa breadboard. Bakit? Kasi sa lab, di ba, si sir, nagdadala siya ng parang tray, tapos you have a ton of resistors, no? So kapag hindi tumama yung bias voltage, kumuha na ng iba, no? And you just need to find the pair of R1 and R2 that gives you the exact VN that you want. But for integrated circuits, for example, no, you don't have that luxury. You integrate the resistor. And that's what you get, no? Once it's printed, yun na yung resistor mo. This is sensitive to changes in R, no? Ultra sensitive, no? Can also be sensitive to changes in the transistor itself, no? That is, nagbabago yung VTH natin, nagbabago yung yung KL, no? So VTH and KL lang naman. Nakalump na yung lahat ng ibang changes, no? So this circuit is extremely sensitive, no? By the way, bakit siya sensitive to changes in the MOS? Kasi nagbabago yung required VIN natin and hindi siya maka-follow nung fixed na resistors natin, no? So how do we address the sensitivity to the change in MOS parameters? We're not really going to address the change in R, no? That's a more advanced thing, no? Because apparently in cutting edge ngayon, resistors na din yung gamit nila for biasing, or actually they can use a lot of resistors now more so than before by by a wasteful technique, no, that we call pruning, I think. But anyway, we just want to fix the sensitive to changes in MOS, no? And simply, given po ba lagi ang Kn? Of course, yes. No? Given lagi ang Kn because it's a transistor parameter. It's something that you would find in the datasheet. Anyway, sige. Ito yung bias circuit natin, di ba? Tapos nakakonect tayo sa gate ng MOSFET. No? So, okay. Ito yung circuit natin kanina. Now, the only change that we'll add is actually we're going to add a resistor here. No? So, we have an RT and an RS now. No? We have R1 and R2. Now, this groundbreaking innovation, as I mentioned earlier, no, I mentioned it for BJTs, now I'll mention it again here. This groundbreaking innovation allows the circuit to be more stable against changes in the MOSFET, no? Now, why is that? It introduces a feedback mechanism, no? Sige. So, paano nangyayari yung feedback mechanism na yan? Sige. Let's say, for example, na-design na natin yung circuit natin. No? We're quite happy with the values that we're targeting, no, for R1, R2, and Bin. Now, kaso, kinuha nung partner mo, yung MOS mo, pinalitan niya ng ibang MOS. Nagbago yung drain current. No? Essentially, what happened is, no, kinuha ng partner mo yung MOS mo, tapos, yung drain current, no, drain current ID, no, yung pinalit niyang MOSFET, yung Kn mas mataas, no? So ID went up, reducing your swing, no? Bakit? Bakit magre-reduce ang swing kapag tumaas si ID? Well, for example, no? We were at B. Tumaas si ID, would be somewhere here. Oh, well, okay, sige. It's better to discuss that here, no? Ayun, no? Sige, ito. Kita nyo dito. Kapag tumaas si ID, we're in danger of going to the linear region because we travel diagonally up to the upper left of the load line. Diba? So then what happens here is something we don't want, no? Because this is in danger of putting our MOSFET to linear. And I believe sa lab it's always a danger, no? To put the transistor in linear where you lose most of the gain or nagdi-distort yung signal, no? And so, no, kapag tumaas si ID, kung nandito ka sa former circuit natin, wala kang magagawa, right? Kasi tumaas si ID, okay, ano mangyayari doon? Kaso dito sa bagong circuit, no? Let's place RD and RS here para makapagsulat tayo dun sa kabila. Yung ID, no? Since umakyat siya, kaso meron din tayong ID dito. Note that the MOSFET gate is not connected at all. Wala tayong KCL dito. This is not a BJT. It's a MOSFET. This is completely this is completely decoupled, no? Some people even call this IDS. Kasi it's a drain to source current. It doesn't matter if you're looking from the source or the drain, no? It doesn't matter. You still get ID down here, no? And when that happens, what you do, what the ID does, no? Here is it causes a voltage drop across the RS, no? And what this voltage drop does is effectively it decreases VGS, no? Which decreases ID, right? It's a negative feedback loop, no? And that's why adding RS always makes the circuit more stable. But you'll see from small signal analysis na babawasan nito yung gain, no? But so that you don't lose your hair trying to pick the perfect MOSFET and so that it works when you show it to the prof, no? You usually do this kasi nakakaubos ng hair kumanap ng perfect MOS na tama yung parameters. Dito, it depends much less on the MOS and it depends much more on RD, R1, R2, and RS yung gain mo, no? So, does anyone have any questions about how this feedback happened? Again, no, the feedback happens kasi tataas yung ID mo. For example, no, tumaas yung ID mo dahil sa pagbabago ng MOSFET, no? Because, you know, even if hindi sinwitch ng partner mo yung MOSFET, I guarantee you, some of you will make circuits tapos you just, you know, go to the bathroom for like 5 minutes. Pagbalik mo dun sa circuit, hindi na gumagana. And that's because the MOSFET is, you know, sometimes temperamental. And to be honest, it's just probably my imagination. They're not supposed to be so temperamental, but I feel like they are, no? Anyway, nagbago yung MOSFET natin, tataas yung ID. Dahil tumaas yung ID, tataas yung VRS, no? Kasi this is ID times RS, no? Yung VRS. Tataas yung ID times RS, which lowers our VGS, no? Bakit? Kasi ito yung loop natin, no? Fixed yung V-in dito. So since fixed yung V-in, tas tumaas ito, no? Bababa yung VGS, which lowers our ID, no? So that's the feedback loop that we get from this, right?
Who is always watching? I think someone is calling, but what? I don't know about minus one. What? No?
Right?
No?
Sige, so let's move on to my personal favorite lesson of this. To be honest kasi okay, my favorite lesson would be the first few weeks of the course. But it used to be 2 courses, no? So ito yung favorite lesson ko dun sa other course, no? It's called current mirrors, no? And this is really cool kasi sige. Let's say no that I have a current source here, no? Ano bang ginagawa ng current source? Well, gumagawa siya ng current, no? Kaso, kinonect ko siya sa isang MOSFET, no? So, ano nangyari dun sa MOSFET, no? Well, this MOSFET will be creating a VGS according to the equation Kn over 2 VGS minus VTH squared, no? Well, actually you do this, no? Such that it goes into saturation. Right? So, yung Kn over 2, this is your ID, no? So, solving for the other side of the equation, Square root of 2ID over Kn plus VTH would be your VGS, no? So this is the VGS you need to create this ID, no? So, saan natin pwedeng gamitin tong VGS na to? Well, just so perfectly, no? Just so perfectly, this gate does not have any current, no? It doesn't load at all the other MOSFET. So we can just borrow the VGS, di ba? Right? We can borrow the VGS of here and give it to the other MOSFET to get an exact copy of the drain current that you put into this side on the other side, no? Kasi if these two MOSFETs, no, have the same Kn and have the same VTH, then you're done, no? So long as they're matched, this ID passing through this MOS, no, produces a VGS on this MOS, and all you need to do is connect this thing like this, no, to this MOS, and you get an ID, no? So this is actually a biasing technique that's used everywhere, no? This is like the most legitimate biasing technique that you have, no? Now, how do you make an ID? Topic for topic for it's a more advanced topic essentially, no? So essentially in most op-amp circuits, ID is transferred from somewhere else, no? ID is basically mirrored from somewhere else. Tapos meron kang isang malaking current source dun sa left side. Actually, sige. Babalik ako dun sa first diodes, op-amps. Sige, wait lang.
Quite shy. Your blog is like a video version of you. And we're talking. Thank you so much for the
So, no? This is the example of an op-amp that we had before. And you can see, no, BJT yung gamit niya kaso ay na-current mirror pa din niya. Meron ka lang tayong konting loading kasi may pumapasok na voltage dito. But, okay, let's point out, no? This thing is a current mirror. This thing is a current mirror. This thing is a current mirror, no? You know, like, kita mo, tinransfer niya yung current bias netong dalawang to. Itong current na to bumababa siya doon. Tapos, kinopya niya yung VBE neto papunta dito, no? These two have the same VBE. So that means this current is that current plus that current, no? Tapos they further transfer it here, no? Naka-current mirror din to. Kokopyahin neto yung current. So this current is also the same. Tapos naka-current mirror din dito. So this current is also the same, no? So naka-bias siya dito sa parang common source na to, no? So that's the current mirror is used in cutting edge circuits, no? In your op amps you will find the current mirrors. All right? So yeah, that's okay, that's that part, no? It's quite a short part, no? Sige, ano. So apparently I'm supposed to discuss the case na magkaiba yung dalawang MOSFET, no? So if you may remember, no? Sige, let's say na KN1 to. KN1 to, tapos KN2 dito, no? Kaso parehas sila ng VTH, no? So let's discuss this case, no? So ang magiging equation natin dito sa taas, no? Sige, this is I Let's call this ID, and let's call this the reference current, no? So the reference current is 1/2 Kn 1 Kn1 VGS minus VTH squared, no? ID is 1/2 Kn2 VGS minus VTH squared, no? So if we wanted to find the ratio between ID and Iref, no? Which, if this is current mirror, this would be 1, right? We get that we just have to put a divider here. Tapos switch natin yung 1 and 2. And we get this, no? So of course, magka-cancel yan, no? The ratio of the output current versus the input current is exactly Kn1 over Kn2, no? Which means that if this were sister MOSFETs, they would have, this would be an actual current mirror, no? Kaso, we can also consider this a current attenuator. Kasi, remember, Kn is, no? Kn is, sorry, baliktad pala, no? 2 over 1. Yan, 2 over 1. Sorry, yeah. Bakit binaliktad ang Kn1 and Kn2? Hindi, well, okay, tama, binaliktad siya. Kasi kinopy-paste ko to, di ba? Tapos binaliktad ko yung dalawang subscript. Kasi ID is this one, Iref is this one, di ba? So Iref becomes this, ID becomes this, no? So yun lang naman yung ginawa natin. It's just that I tried to change it, but I wrote the exact same thing, no? So that was my bad. Anyway, since we have Kn2 over Kn1 here, no? We're going to have width 2 over width length 2 mu n C ox with 1 over length 1, no? So we're going to have this. And for a specific fabrication foundry, no? Well, okay. Mu n is the mobility of an electron in silicon, no? Which doesn't change. So we're sure na cancel out yun. Yung oxide capacitance depends on the, di ba, meron kang metal. Tapos meron kang p-type, no? Di ba? The capacitance depends on the width of the dielectric, di ba? And for a specific foundry, they don't usually change that, no? So hindi nagbabago yung COX. So cancel din to. So what we get is that Kn2 over Kn1 is width over length over width over length, no? Of the two MOSFETs. So if ever that we wanted to reduce the current, no, by, I don't know, 10 times, no, then we just have to make 2 10 times bigger than 1, no, 10 times wider. Is most easy. It's the easiest way to do it, diba? If you make this 10 times wider, then ID would be 10 times Iref, no? If Kn1 is 10 times the width of Kn2, then ID would be 1/10 of Iref, no? So that's how useful current mirrors are. All right. So in fact, if you add dito sa calculations natin, if you add channel length modulation dito sa equations natin, sige, just simply add CLM, no? 1 plus lambda 2 VDS um, 2, no? VDS 2. Tapos 1 plus lambda 1 VDS 1, no? Note na magkaiba sila ng VDS, no? V out yung VDS nito, tapos ang VDS nito is equal to VGS. Right? Oh, by the way, no? Can anyone answer this? Bakit sure tayo na bakit sure tayo na saturation lagi itong diode connected MOSFET? Well, actually, kailangan may current source para sure tayo na, para hindi cut off, no? Kaso, why is this never linear? Hmm. This is never linear because VGS, tama, no? VGS is equal to VDS. And we want VDS to be greater than VGS minus VTH, no? So really, the only condition that remains, no, is that VTH has to be positive, no, which it is, right? For NMOS at least, no? May magbabaliktad dito sa equation to. So parang for for PMOS, this would be what happens, and sure enough, what you get from here is the absolute VTH has to be greater than 0, which is also always true, no? So this is the reason why we are guaranteed saturation in this guaranteed saturation for a diode connected MOS. All right. And with that ends ends the lecture for today. No? So sige. With that, no, we end like around 30 minutes early, which is nice. And sige. So with that, I'll see you guys next time to discuss and discuss natin next time. MOSFET amplifiers, no? So yung topologies, no? Common source, common gate, and common drain, no? Sige. So yeah. I'm not going to be posting a specific video recording. Well, okay, may recording tong class na to. I will post that, but I'm not going to be recording like a separate one anymore because I thought about it and it turns out now we have enough time to cover. So we will finish the coverage of midterms by Friday, and um we will proceed to we will proceed to oh, we will proceed to um ang tawag two-port networks next week, no? I won't be taking attendance for today, no? So sige, yun lang, no? So with that, thanks guys for attending and I'll see you guys on Friday.